Okay, y reswm chi wedi cael gwahanu heddi yw oherwydd tua mis ar ôl ni gofyn i chi os oes diddordeb gyda chi astudiannau lladd gwyddorau neu mathemateg yn y chweched dosbarth. A ni'n hynod y lwcus heddi i cael Dr Ben Evans a'i griw o Brifysgol Abertawe ar adran Beirianeg i roi'r ochr sioe i chi heddi. Just explaining that these students have expressed interest in studying either sciences or maths at A-level. And as you know, for our country to compete in today's technological world, we need more than ever scientists, mathematicians and engineers. So hopefully these will be the future, and perhaps we'll be down with you in Swansea University in 3 years' time, hopefully. So I'll pass you over to Dr Ben Evans and his team.
Diolch. Wel, pnawn da, dwi'n dysgu Cymraeg. Felly, well, dwi ddim yn rigol eto, but soon I will be, because I'm married to one of the teachers here, and I'll leave you guessing who that is, and she's trying to get me to speak Welsh. But I'm going to do this session in English, if that's all right with you. Yeah, you're all guessing who it is, right? Shall I just tell you, so you don't... Can you guess? No. Yeah. Mrs. Tootle. She teaches English, yes. So, what we're going to do, I've given you all a piece of paper with a couple of questions on it. So just before I say any more, I'd like you to, without thinking about it too much, there's no right answer, wrong answer, I just want to gauge people's perceptions of the question in front of you. So the two questions are, what is engineering, because I am an engineer, and what do engineers do? Okay? I just like to find out what you guys think are the answers to those questions. Okay? This is David, he's one of my students at Swansea University, and this is Reem, another one of my students who will be helping me out this afternoon. And we're going to learn about a project that you may have heard about called the Bloodhound Supersonic Car Project. How many of you have heard about this project before? A couple of you. Okay, cool. Well, you're all going to know about it in 45 minutes. So I'm just going to give you a minute to answer those questions, and then we'll carry on. Okay, you've got 30 seconds left. Even if it's just a couple of words you put in the speech bubbles. And it was actually, incidentally, I'd forgotten this, it was Mrs. Tootle who drew those little pictures for me. Because she's a much better artist than I am. Okay, so, as has already been introduced, my name's Ben Evans. I work at Swansea University, and my background is that I'm an engineer. I'm actually an aerospace engineer. Maybe a little bit later on I'll explain exactly what that is about. I've been involved in a project that I think, I'm a little bit biased, but I think is one of the most exciting engineering projects happening in the UK right now, possibly anywhere in the world. What we're trying to do is design the world's fastest car, okay? So that's what this is, okay? We're designing a car that's called the Bloodhound Supersonic Car, and that's what this project is all about. To give you a little flavour of what is going to be happening over the next couple of years as we start testing this car, I'm just going to show you a short movie to get things started.
This is the most extraordinary project I have ever been involved in. what we're doing is creating the most advanced land speed record car that's ever been built. Bloodhound SSC has a very unusual objective for a land speed record project. It's not to set a speed or even a new record. It's to get everybody from 6 to 96 years old, interested and excited by mathematics, engineering, science, technology. The objective here is to share the project and all its technology as widely as we possibly can. But the key thing to all this is education. Whether it could be bridges, whether it could be fashion, it could be fast cars. People love engineering. I am a Royal Air Force flight pilot, but first and foremost, I'm a mathematician. And that is a way I not only think about numbers, incredible numbers involved with flying fast jets from day to day, but also the truly astonishing numbers that Bloodhound SSC is throwing up. Just to give you an idea, the bodywork at these speeds has got to take loads of the order of 12 tons per square metre. I mean, it's got to be as tough as a submarine. Nobody's ever done anything like this before. When we are accelerating this car, it's going to be peaking at 3G, 60 miles an hour per second. At peak speed, it will be covering the length of 4 football fields per second. The wheel rims will be experiencing 50,000 radial G at the rim. Those sorts of numbers are truly astonishing, and if you don't understand them, truly frightening. And as the driver, actually that's not a good thing. I'm in the lucky position, as the world's fastest mathematician, of being able to understand and be comfortable with those numbers, understand the engineering solutions.
We have to remember that this is an adventure. It's an engineering adventure. We don't know what the final outcome is going to be. And even if we don't get to 1,000 miles per hour, it won't necessarily be a failure if what we have done is inspire people.
There's going to be a huge industrial revolution. And to cope with this, we've got to have the scientists. We've got to have people studying mathematics, science, engineering. Because basically, unless we do this, Britain simply isn't going to be able to play.
Okay, so yes, that was me from a few years ago when we launched this project in London. And as Mr. Lloyd has already pointed out, and he's absolutely spot on about this, the reason we're doing this project isn't just because we want to get a car to go fast. We do want to get a car to go fast. But we're doing this for you guys. We're doing this so we can share what engineering is all about, what you can do with science and technology and mathematics, because the UK desperately needs engineers, okay? At the university, we work with a lot of big companies, and all of them are saying to us, in the next 20 years, there's going to be a massive shortage of engineers and scientists in the UK to work at places like Airbus and Rolls-Royce, companies like that we work with. So I'm going to test you here a little bit. Before I talk about the car that we're designing, we want to go back in time a little bit. This is arguably the first car, or the first vehicle that nowadays we would describe as a car, okay? This is from the end of the 18th century. It's a steam locomotive. Does anybody want to have a guess at what the top speed of the world's first car was? Any ideas? Don't know, shut up. What do you reckon? 10 miles per hour. Who thinks it was higher than 10 miles per hour? Your hand if you think it was higher than 10 miles per hour. There's no right or wrong. Well, there are right and wrong answers, but you're not going to get any marks for this. Who thinks it was lower than 10 miles per hour? That's all of you. Yeah, you guys are right. It was actually 2 miles per hour. So the world's first car, a steam locomotive. It was used for carrying heavy weapons, and it moved at about this sort of pace, a slow walking pace. If we fast forward 100 years or so, we meet this guy. This is a Frenchman. His name is Gaston. And one of the things we're trying to do with this car is get our name into the Guinness Book of Records. I'm sure loads of you have a Guinness Book of Records. When I was a kid, I used to get it for Christmas quite often. And in here, if you go to the page, which is the World Land Speed Record page, you will find this guy's name at the top of the list. He was the first man to create a car specifically designed to go as fast as it possibly could do. It was an electric-powered car. Does anybody want to have a guess at how fast Gaston's car is? This is an electric-powered car driven in Paris, the end of the 19th century. Any guesses?
Laura's. Heard some good numbers.
Yeah.
So not long.
15 miles per hour, and now you're being pessimistic, you see. By this point, this is 100 years later, and now we had a car that travelled at 39 miles per hour, which I think is amazing, actually, when you think that today engineers are trying to figure out how we can be driving around in electric-powered cars, because that's the way we need to go. We need to get off burning fossil fuels and towards electric-powered cars, and we're really struggling to come up with good solutions to this problem. Of course, since then, cars have got faster and faster and faster, and I'm sure all of you drive around regularly in cars that go faster than Gaston's electric car. But in terms of the land speed record, things started getting really interesting in around about the 1950s and 1960s. Because at that time, they realised with conventional wheel-driven cars, they'd about reached the limit for what cars could get to. And that was about 350, 400 miles an hour, okay? So they started, and this is really when things got exciting, putting jet engines into cars, okay? So from the 1950s and 60s onwards, land speed record cars had jet engines and rocket engines inside them. This is the Thrust 2 car. Back in 1983, around the time I was born, was travelling at 633 miles per hour. And this one here is currently the world's fastest car. This broke the land speed record in 1997. It's called Thrust SSC, okay? And its top speed was 763 miles per hour. So the world's fastest car today is not the Bugatti Veyron, which is what lots of people think it is when I ask this question. It's actually this car here. It crossed the Nevada desert in America, just a little bit faster than the speed of sound. And I'm going to explain the significance of that in just a minute. But what we're doing with this car is ridiculously ambitious. We're trying to take the world land speed record from 763 miles per hour to 1,000 miles per hour. We actually think that the car will achieve a top speed of 1,050 miles per hour. That is blinking fast, okay? Like that's proper scary fast. And sometimes it's the thing that keeps me awake at night. So in terms of the history of the land speed record, here are some of my favourite cars. We've got Babs and Bluebird. These are actually my favourites, or some of my favourites, because these broke the land speed record just down the coast in Pendine. In fact, in the summertime, if you go to Pendine, they've got a museum and they've got a restored version of Babs there that you can actually see in real life, and it really is amazing. And of course, hopefully what you can see from this is if this is the current land speed record, taking it all the way to 1,000 miles per hour is incredibly ambitious. But I think that's why it's exciting. And it takes us into this regime of aerodynamics. Now this is what I do my research in the university, in aerodynamics. Does anybody know what aerodynamics is? Anybody? Yeah.
Well, when you try to cut through the air, make it more, so the air doesn't catch.
Yeah, absolutely. It's all to do with flow of air. Okay, so aerodynamicists trying to understand how a car or an aeroplane flows through the air and what the air does to it. Okay, and there's a regime of aerodynamics called supersonic, and basically supersonic means we're travelling faster than the speed of sound. And what I'm going to try and do in about the next 5 minutes, okay, is quite ambitious as well as designing Bloodhound, because I'm going to try and explain to you some ideas that usually we take a whole module of a university course to teach. Okay, and I'm going to try and explain this to you in 5 minutes. So you two need to listen in as well, because this will help you pass your exam. Now, we drove here today from the university in a Ford Focus. Okay, I know it's hard to believe that I'm designing the fastest car in the world, but I drive the Ford Focus. And that was definitely what we would call a subsonic vehicle. Okay, it travels slower than the speed of sound. How did you all get to school today? How many came on a bus? How many walked? How many came on a bike? Nobody. Did anybody come in a vehicle that was supersonic? I doubt it very much. Okay. So when we travel around, you and I, in everyday life, we're travelling slower than the speed of sound. So as I was driving here today through T Cork and Cocket, what was happening was the front of my car was disturbing the air in front of it, okay, pushing it and creating a pressure wave. Okay, pressure waves and sound waves are the same thing. Okay, so as I'm talking to you now, my vocal cords are creating pressure waves. They're coming out of my mouth and they're flying across this room to your ears, and they're travelling at the speed of sound. Does anybody know roughly what the speed of sound is?
Shout it out, you can be wrong.
Yeah, go on, shout it out. Yeah, not far at all. On a day like today, it's quite cool. It probably isn't far off 750 at all. It varies slightly with the temperature. So actually, on the day when they ran Thrust SSC in America, it was more like 760 miles per hour, because it varies slightly with the temperature. But you're spot on, okay? So those sound waves my car is creating, and I'm creating now as I walk across the room, and as I talk to you, okay, are travelling at 760, 750 miles an hour. So they get to you, and it almost feels like they arrive at you the same time you see my mouth moving. But there's actually a little bit of a delay. You guys at the back hear me a little bit later than you guys at the front, okay? And what those sound waves do when we're travelling forwards in a car is they basically tell the air ahead of us that we're coming. So as I'm driving along the road, okay, and David is there ahead of me, okay? My sound waves, the pressure waves, are telling David, if he's an air molecule, Ben is coming in his forward focus, you need to start moving out of the way. So you start moving out of the way. So he does it in advance, he knows I'm coming, okay? Obviously the air doesn't know my name and the make of the car, it just knows that something is coming, it needs to start moving out of the way. And that's what's happening here in the kind of world that we live in, subsonic, slower than the speed of sound. Now, and this is where things get confusing, and this is where we spend a lot of time trying to explain this to students at the university, so hang in there, okay? As we get faster and faster and faster, and start approaching the speed at which those sound waves travel, eventually it gets impossible for David to know that I'm coming. Because if I'm also travelling at 750 miles per hour, and I send that wave forward at 750 miles an hour, but I'm also travelling at 750 miles an hour, I'm just travelling at the same speed as that sound wave. So it becomes impossible for David, the air molecule, to know that I'm coming. So instead of everything happening nice and smoothly like this, everybody's happy, the air molecules move out of the way, the car moves through the gap that the air molecules have created, we create something, okay, that only gets created when we travel faster than the speed of sound. Does anybody know what that thing is? I'll tell you a story which may help, okay? I grew up in Mumbles, and in the evening, I used to go for a walk around the cliff path with my dad, and at around about the same time every evening, it was about 7:20 every evening, there would be a loud bang overhead, okay? Almost exactly the same time. Sounded like a clap of thunder, but it was kind of like a sharp clap of thunder. Anybody have any idea what that might have been? Somebody's saying it, I can hear it. A sonic boom, absolutely. Does anybody know what aircraft was creating that sonic boom? I'll be well impressed if you know. Yeah, somebody said it. Yeah, Concorde, okay? Because back in those days, there was a supersonic plane that people like you and I, if we had enough money, could fly on. I remember the adverts on TV, okay? The advert said that you could take off from London and fly to New York and land in New York before you left London. Because actually the time it took Concorde to fly between London and New York was less than the time difference between the two. So like rich businessmen would do a day's work in London, jump on Concorde, fly to New York and have dinner in New York. That's pretty cool, isn't it? Unfortunately, you can't do that today. And that sound that I heard overhead was the sonic boom of Concorde as it flew overhead. So that was the London to New York flight that would have been in New York in about another 2.5, 3 hours, which is pretty amazing. So what we've had to do with Bloodhound, of course, because it's going to be travelling faster than 750 miles per hour, it's going to be travelling about 30% faster than the speed of sound, we're going to be generating these things called shock waves. Okay, these very sudden compressions in the pressure of the air. So the pressure suddenly jumps up because the air has had no warning that the car will be arriving. We know what these are like. I'm going to show you a movie here of a supersonic military fighter passing a ship, just so you can see these guys they know this is about to happen, so they've got their hands in their ears. So that's what one sounds like. But we can actually create one right here, and David's going to help me out. Now, what I'm going to ask is if, can you two guys here possibly, just for a moment, stand up and kind of slide in that direction? In fact, could you four stand up and just slide in that direction? I just want to measure the length of this. You hold it up. Okay, we're going to be fine. Because, believe it or not, how many of you have seen Indiana Jones? And what noise does the whip make? Yeah, it's that kind of sound. And that sound you hear is actually a shock wave that's created when the tip of the whip travels faster than the speed of sound. So I'm going to try and get... It's not easy to do it, actually. Indiana Jones makes it look very easy.
Exactly. Try your best. See how it works.
There it is. Give him a round of applause. That was quite impressive. That's not easy to do. If we got time at the end, I'll let some of you have a go. You can sit down. So that, I just didn't want to take your eyes out. So that noise there, the tip of the whip, was actually travelling faster than the speed of sound. In fact, you may be thinking, I don't believe that, okay? And it's a really interesting physics problem, actually, how you get from the tip of your arm, which maybe is travelling at, I don't know, 60, 70 miles an hour, to the tip of the whip, travelling at 800, 900 miles an hour. And you can ask Mr. Lloyd how that happens later. So the question is, we've got all of this complicated aerodynamics. We've got shock waves, we've got supersonic flow. how on earth do we make sure that this car is going to be safe? Because we're going to put a guy in it, and he's a good friend of mine now, a guy called Andy Green. You saw him in that movie. He's going to drive this car next year, hopefully at 1,000 miles per hour. So how do we do that? Well, traditionally, we would have used what you see on the left-hand side there. Who recognises what we've got on the left-hand side? Yeah? So we've got a Formula 1 car inside a wind tunnel, okay? It's quite a big, sophisticated wind tunnel where you can roll the ground underneath the car, rotate the wheels of the car. And maybe 20 years ago, that's how you'd have had to do all aerodynamic analysis. But in the last 20 years, we've developed a method, and Swansea University has been at the heart of this, called CFD. Does anybody, and I'll be well impressed if anybody knows this, does anybody know what CFD stands for? Has anybody even heard of CFD? No. Occasionally, they mention this on the Formula 1 coverage. I've noticed this, that David Coulthard and his friends, they'll talk about sending the design back to the factory and getting the guys to do a CFD study. And I'm sitting there at home thinking, I'm pretty sure most people have no idea what you're talking about right now, David. So you guys are going to know what you're talking about. CFD stands for Computational Fluid Dynamics. And that's basically what I and David do our research in, okay? And what we're doing is basically what you would normally do in a wind tunnel, so aerodynamic studies, but in a big supercomputer. And again, what I'm going to attempt to do in the next 2 minutes is teach you something that normally we would take an entire term to teach a bunch of undergraduate students at the university. So what I would like you to do, okay, don't panic, this is where we're going to have a little bit of maths, okay? What I'd like you to do is put your hand up in the air if you think you could solve that equation there. So we got 4 times some unknown u is equal to 12. I won't even ask you for the answer, I just want you to put up your hand if you think you could solve that equation. Keep your, yeah, Mr. Lloyd, you should really have your hand up. Keep your hand up in the air if you think you could solve those equations. So when I was in school, we used to call these simultaneous equations. Is that still what you call them? Or in a Gymraeg? How do you say it in a Gymraeg? Oh, yeah, that. Keep your hand up if you think you could solve those equations there. So by this point, probably at this point, you're thinking, yeah, we're going to have to do a lot of algebra and throwing variables around and taking things to the left-hand side. Keep your hand up if you think you could solve those equations. We've got 1, 2, 3, 3 or 4. Now, can you see what's happened here? As the number of unknowns has gone up from 1 initially to 2 and 3 and now 4, what's happened to the number of equations we have? It goes up. Okay, so to solve for 4 unknowns, which is what we've got here, we need 4 equations. Now, in the world of aerodynamics, there are always 5 unknowns that I'm trying to solve for. Okay? I'm trying to work out what the density of the air is, because that's something that can change. I'm trying to work out what the velocity of the air is. Okay? And an air can move in 3 directions. It can go in that direction, that direction, that direction. Okay? So there are 3 components of velocity. And I'm trying to work out what the temperature of the air is. Okay? So there are 5 unknowns. So, how many equations do you think I need to solve if I've got 5 unknowns in my problem? 5. Well done. The problem is, my equations don't look as simple as that. Now, you may be looking at those thinking, well, they don't look particularly simple to me, but trust me, things can get a lot worse. Now, if you genuinely have a phobia of mathematics, okay, just cover your eyes for 30 seconds, okay? Because I'm going to show you the equations that we solve every day down in the university. Okay, this is what they look like. Yes, they're horrible, aren't they? If you look at those and you think that looks absolutely horrific, well, you're absolutely right. It is absolutely horrific. There's actually a maths institute in America right now offering a $1 million prize to anybody who can come up with an exact solution to those equations. Okay? But they come from some quite simple principles, and principles that you may have heard of in science already. So conservation of mass might be something that you've heard of already. Conservation of momentum, is that something you've come across? I don't know what you call it in Welsh, yes?
Yes, the 6 farmers definitely with that.
Some of them, and conservation of energy. So they come from some quite simple principles, but when you write them down as maths, it looks horrendous. So what we do is we use that big computer to solve those equations for us. Okay, and that's basically what we're doing in CFD. I'm going to fast forward for you because I really want to get on. I'm going to fast forward. Okay, in fact, I'm going to fast forward because I want to show you. Okay, I want to make sure we talk about the engines because I think this is really exciting. So, does anybody know what engines we've got inside Bloodhound? Does anybody want to guess what we've got? What engines we've got inside? So we've got a jet engine. Okay, so we've actually stolen the EJ200 jet engine out of the Eurofighter Typhoon. Did anybody go to the Wales air show thing that was in Swansea this summer? Yeah. And the Eurofighter Typhoon was one of the real stars of the show, and it was blinking noisy. Okay. The Eurofighter Typhoon has 2 of them. We've stolen one. Okay, it's that thing there. We haven't stolen it, so you think that's a bit of a weird thing to do. And we asked the MOD if we could have one, and they gave us 3, which is very nice of them, I thought. And we're going to be putting one of them in the car and keeping the other 2 as reserves. This is what it looks like. I'm just going to show you how it works. Now, most people have got a kind of vague idea of what a jet engine does, because you've seen them hanging off the wings of aircraft, for example. So basically, you've got a fan at the front, which is sucking air in. It's compressing it. If you compress air, basically its pressure goes up and its temperature goes up. And then you pass this compressed air into a series of combustion chambers. And this is the point where we add the fuel. So we squirt the fuel in, it gets ignited, and because of that chemical reaction, the temperature and the pressure goes up even higher, and all of these hot gases have to expand somewhere. So they expand out of the back of the engine through a turbine, and that turbine is connected via a shaft here, which is driving the compressor at the front, and the whole thing just gets faster and faster and faster. You're kicking air out of the back, and if you're kicking air out of the back, you're pushing the engine forward. Again, that's like a 30-second description of something we would normally take about a term to teach an undergraduate student at the university. But that's how a jet engine works. And our jet engine, the EJ200, generates 9 tons of thrust, or 90 kilonewtons of thrust in new money. If you fast forward that, you can see that on the internet. But that's not enough for us, okay? So what we've had to do, and this is where David's going to help out with a little demonstration, is design the UK's largest ever rocket, which is also going to go in the car, okay? So we've got a jet engine, and underneath the jet engine now, in the design of the car we've got this rocket engine. And what we're going to do is demonstrate what is happening inside the rocket engine when we fire it, okay? Now, how many of you study chemistry, or have studied chemistry? Yeah, some of you, okay. How many of you know what the chemical symbol for hydrogen peroxide is? If I were to tell you that a molecule of hydrogen peroxide is basically a water molecule with 1 additional oxygen atom attached to it, could you work out what the chemical symbol is? H2O2, okay? So hydrogen peroxide is H2O2. Well done, I'm impressed. Excellent. Now I reckon some of you use hydrogen peroxide for something. In fact, I'm pretty sure you do. Does anybody have any ideas what some of you might use hydrogen peroxide for? Hair dye. So if you want to bleach your hair, you will use very low concentration hydrogen peroxide and put it in your hair, okay? What we're going to do in the rocket of Bloodhound is pump 99% concentration, so that's 99% hydrogen peroxide, 1% water, into the rocket engine. And what we're going to demonstrate here is how that works. Now again, what I think is probably going to be wise to do is if you 4 here, sorry, this is the price you pay for sitting in the front row, could you just possibly get up and stand over with these guys over here while we do this?
If you need to see, stand up, my arm is saving, right in the head,
now,
it's sort of wrong the
hydrogen peroxide is not a particularly stable substance. Okay? Hydrogen peroxide wants to break down into 2 other chemicals. Any ideas what those 2 chemicals are? It's not hydrogen and oxygen, because if hydrogen and oxygen came into contact with each other, we'd have a big bang. What are 2 stable substances that we see everywhere that kind of made up water and oxygen? Okay. So when this breaks down, okay, we're going to see water produced, and we're going to see oxygen produced. So if oxygen is going to be produced, what are you likely to see here, do you think? Bubbles. Now to make it a little bit more interesting, what we're going to do is add some fairy liquid to the test tubes, just so those bubbles turn into foam, okay? And what we'll do first of all is, let's move this out of the way in case the first one triggers the second one. So we're going to get this to start, we need to add a catalyst. And what does a catalyst do in a chemical reaction? Speeds it up, okay? So just to get this started, we're going to add a catalyst. And lots of chemicals act as a catalyst for this reaction. One of them is sodium iodide. So we're going to add a little drop of sodium iodide solution, not all of it, because we need to save some for the second experiment, like here, and we'll see what happens. Fingers crossed we got this right. And what can you see coming off the top of this? In fact, it's really hot. So what type of reaction is it? Excellent. This is brilliant. Well done. You've been very good. So just like in the jet engine, the whole point of doing that, okay, was to get the pressure and the temperature to go up. All of these exhaust gases want to expand. They expand out the back of the rocket, pushing the rocket forward. But the faster we can get them to exit out the back of the rocket, the more thrust we generate. And we can show how we model basically the end here, where you've got a little nozzle, by doing exactly the same experiment with the same amount of hydrogen peroxide. And I've never actually tried this, so I'm genuinely interested to see
So
this.
look how it works.
Have we added fairy liquid?
We have.
Yes.
It's all
Okay.
in there.
So we're going to add about the same amount of catalyst, same amount of hydrogen peroxide into a tube with a narrower funnel, and we'll see what happens. Hopefully we're not going to hit the roof. Okay? So actually, the energy stored in that reaction, exactly the same as the other one, but because we had a slightly narrower tunnel, we'll clean your computer for you, don't worry. And we'll wipe those off the roof. Okay, you can all sit down. Can I just ask, when it gets to the end, please don't come and touch this. It's perfectly safe. Actually, this is basically foamy water now. But this stuff down here is stained with iodine, which can stain your clothes, so don't come and touch it at the end. So that's what's going on inside the rocket. We just decomposed about 50 mil of hydrogen peroxide here. In our rocket, we're going to be pumping 1 ton of this stuff into the rocket, at about 3 times the concentration of this. And the result will look something like this. This is actually a half-scale rocket that we tested last year. We've now tested the full-size one, so just this will give you an idea. So you imagine being Andy Green, the driver, who's sat on the front of that, which generates 12 tons of thrust. That's about the weight of an elephant, okay? And a jet engine on the top of that, and you're accelerating down the desert, approaching 1,000 miles per hour. So, how do you design a supersonic car? This is what we've been doing for about 5 years. And the story of this is all on the Bloodhound website, which is bloodhoundssc.com. But basically, what we've done is what's called design iterations, okay? So we took an initial concept for the car back in 2007, and we asked the question, probably the question that those guys who designed the world's first car asked. What are the problems with this? What are the things that are wrong with it, and how can we fix that? And then we fix those problems, and we look at a new design of the car, and then we say, okay, what are the problems with this? How can we improve this? And we create a new design. We call that design iteration. And we've gone through actually about 12 different designs of the car to bring us to this design here, which is the car now that we're actually building. It looks like this. This is the colour scheme. I don't know if you like it or not. When they first agreed on the colour scheme for the car, I told all the other engineers I thought it looked like a Dyson vacuum cleaner. I don't know what you think, but the colours have grown on me now. And actually, Swansea University, which of course has half the logo in Welsh, is on the side of the car. So Welsh will be, for a moment, one of the fastest languages in the world for a few seconds. Yeah. This is how the car is being built. So the front half of the car is a carbon fibre monocoque, a little bit like a Formula 1 car. So the actual stresses that are carried through the structure are carried through the skin of the car itself. And then at the back of the car here, we've got an aluminium and steel and titanium space frame, basically supporting all the systems at the back of the car. Now, have we got, how long? We've got about 6 minutes, have we?
Yeah, about 6
Okay, so some of you may be thinking at this point, okay, so all you've got to do is go as fast as you can, which means you're probably going to be just going in a straight line, and I've seen Top Gear, that's easy. So what I just want to show you is the movie footage of Andy Green, who will also be driving our car. This is him breaking the land speed record back in 1997 in the Thrust SSC car, just to give you an idea that actually driving this is not going to be straightforward. So on the right we've got a view from the tailplane of the car. On the left obviously is his hands on the steering wheel inside the cockpit. In just a minute, you may be able to just make it out now, you'll see a white line that's been painted on the desert floor, and Andy is trying to keep the nose of the car right on that white line. The initial acceleration is actually quite modest. He's probably still only doing about 70, 80 miles an hour at this point. we can't throttle the engines up straight away because we would just suck in lots of dust off the desert surface. So we slowly ramp up the engines. And in a moment, you'll see that he likes the afterburners. How many of you have seen Top Gear? No, not Top Gear, Top Gun. If you haven't seen Top Gun, what kind of education is Bryn Tower giving you? Top Gun is one of the greatest movies ever made. And Tom Cruise is in it, yeah. So here are the afterburners lighting up. Tom Cruise talks about the afterburners quite a lot in Top Gun. This is where we're squirting fuel into the exhaust of the jet engine, so you're getting a second lot of ignition. We'll get the picture back on the right-hand side. We're now up to about 400 miles an hour. This is where Andy has a massive problem, and he goes off the line by about 20 metres. He's now going to about 600 miles an hour. Look at that, 600 miles an hour, full lock on the steering wheel. 700 miles an hour. And now he's gone through the measured power when he measured his speed. I'm going to stop that there. So actually, just because of how sensitive this car is going to be once it starts travelling at these kind of speeds, Andy is going to be working, blinking hard in the cockpit to keep this on the straight line. So just to finish, I want to talk you through what we think a 1,000 mile per hour run with Bloodhound will look like. So what I'm showing you here on the blue line is acceleration, measured in G. So that's multiples of 9.8 meters per second squared, okay? And the red line is speed in miles per hour. So the initial acceleration, just like on thrust, will have to be quite modest because we can't just put the engines, throttle them all the way forward straight away in case we suck the desert up into the car. But once we get out to over 100 miles an hour, we can light the afterburners, or what we call the reheat on the engines. And you can see, because the thrust goes up, the acceleration goes up, which means the slope of the speed line. Here we go, this is how to teach distance time, speed time graphs. I remember when I did this, when I was in his school in Bishopston, they used to teach us this kind of stuff. And the examples they give us were things like your mum's shopping trip to Tesco's, find the points on the graph where she stopped at the traffic lights. And I'm like, well, that's a way to bore a child. Right, anyway, sorry, we get to about 300 miles, sorry. When we get to over 300 miles per hour, we can light the rocket, okay? And again, the thrust shoots up, which means the acceleration shoots up, which means the slope of the speed line goes up. And by this point, we're only 28 seconds into the run, and we're already travelling at, approaching 500 miles per hour. And then we arrive at the measured mile. So in the middle of the track, the Guinness World Record people will be there measuring our average speed over a mile. And at 1,000 miles per hour, we cover a mile in 3.5 seconds. That's pretty fast. Then, we've got to get the car to slow down, okay? Because our track is only 10 miles long. So if you're Andy at this moment, you're travelling at 1,000 miles per hour, covering a mile every 3.5 seconds, and there's a mountain in 4 miles, okay? You want this thing to slow down. So we've got a series of air brakes and parachutes, which just make sure that the deceleration is slow enough, and actually is steep enough, to get it back to zero in the track that we've got. So I guess in the language of maths, this is a run of the Bloodhound car, 0 to 1,000, back to 0 in 90 seconds, covering 10 miles. Imagine going from here to, say, Port Talbot, maybe it's 10 miles away, in 90 seconds, going from 0 to 1,000 and back to 0 en route. It's pretty impressive stuff. And we think it's going to look a little bit like this. This movie was sponsored by Intel, okay? They don't actually look like that.
Bloodhound SSC, you're cleared. Engine start. Bloodhound engine start. Ready to roll.
Diolch yn fawr. Thank you very much,
So,
Ben.
thank you very much.
Fi'n gwybod,
I'll keep them.
mae